Okay, so I hope we're live now. So welcome to the first session on the ZX calculus, and I will now introduce our first speaker, who is Niel de Beaudrap, who's going to tell us about well-tempered ZX and ZH calculi. Go ahead, Niel.
Okay. Thanks for tuning in. Thanks to the organizers for organizing this and for the opportunity to speak. I did this, of course, at the University of Oxford, where I'm based, funded by a gift from the Chinese tech firm Tencent. Okay, so what's my motivation here? I'm here not as somebody who's the sort of person who would normally do work developing the ZX calculus, but as a prospective user. I see the ZX and the ZH calculus both as good mathematical tools. And I'd like to use them for scalar exact, in other words, equational reasoning about quantum procedures in general, not just unitary circuits and not just for reasoning whether two unitary circuits are equivalent to one another, but for anything. In quantum technologies, for instance, where you might worry about such things as distillation protocols. The problem that I have with this is that they've got a common misfeature for this task, which is the need for frequent bookkeeping of what I'll call scalar gadgets. And it may be clear to you what this means. I'll introduce what this means to you. They're closed diagrams whose job is to represent a scalar factor. And the ones that I mean in particular are ones that don't contribute constructively to the analysis. It's possible to have a scalar gadget which represents the fact that, represents a number corresponding to something which is a meaningful feature of what you're trying to do, a probability of success, for example. However, if you use the ZX calculus in practice and you use it for scalar exact reasoning, you'll notice that you often have scalar gadgets that don't correspond to this. And my personal experience with this is that they clutter the terms that you're trying to work with. They complicate the rewrites if you're trying to reason precisely. And if you're communicating to a broader audience, an audience, for example, that doesn't have a large overlap with the QPL community, it becomes difficult to communicate and you find yourself justifying these. So it sort of has the problem of possibly limiting impact. So it's a small problem. The world has many problems these days. This is a pretty small one in the big scale of things. Fortunately, it's small enough that you can fix it by just doing a little bit of careful tuning of the calculi. Now, I'm not going to talk an awful lot about what these calculi look like. If you want to see what they look like, you can just take a look at page 2 or 3. There are only 3 really important pages in my article, the second, the third, and the very last one. What I want to do is to convince you of the fact that there is a problem and to give you something of an outsider's look at what the ZX and the ZH calculi are like in order to motivate why this is something worth addressing. So the ZX calculus, it hardly needs introduction at this point. That's the original reference. They're string diagrams representing interacting quantum observables. What we mean by observables are, for example, operations in which we have a principal role for 1 or 2 different bases in which you can store information. So we have Z dots, commonly called green dots, in which the standard basis plays a principal role, and we have a phase parameter representing part of the dynamics of what happens in that basis. Here in my diagrams, time runs from left to right, as in conventional quantum circuit diagrams. We have X dots, which are similar to the Z dots, except that the preferred basis for the interaction is the so-called conjugate basis, which is to say the eigenbasis of the X operator. And also the Hadamard, the isomorphism between them. Okay, so of course, wires represent qubits or the states of qubits. Dots and boxes correspond to operators, or more generally tensors, which is what you'd have to say when introducing this to a more general audience in order to get past some of the fact that some of these no longer represent operations which you intend to act on the qubits, and I'll touch on that in a moment. Of course, we connect these things together by sequential composition. We connect wires, and this makes our tensor dots turn into tensor networks. Operations can act on different systems in parallel. This is a story that we all know fairly well. Okay. So concretely, what these dots represent. So we've got, of course, this operator for Z dots, again, sort of preferring the standard basis, as I alluded to, and introducing a phase on the component having to do with the 1 state. Same story for the X dots, only with the plus and minus basis. And the Hadamard needs no explanation. It's the unitary transformation. Okay. Why are these operators? You might ask if you were coming from it afresh. The answer that's sometimes given is that the phase-free nodes form special commutative Dagger-Frobenius algebras. And if you know what these things are, this is sort of reason for celebration. These are well-liked things, but for people who don't come from these foundations of logic background. Some explanation is needed. So what's so special about these special commutative dagger-Frobenius algebras? It's that these operators single out classical structures. They describe how data can be stored and copied in particular bases. So here are the two families of operators, the green and the red. They express different choices of basis, of course, the standard basis or the conjugate basis, and they distinguish the elements of the basis. They distinguish the 0 from the 1 in terms of the dynamics. They distinguish the plus from the minus. And if the arity is greater than 1, they all have operator norm 1, which is not how it's commonly described. We don't often talk about operator norms in this community, but this is pretty important from an operational standpoint. It means that, for example, the degree 2 nodes, 1-to-1 nodes, are unitary transformations. 1-to-2 nodes are isometries, so they're not bijections, but they represent valid evolutions of a quantum state, which you could do in principle deterministically. They introduce a new qubit. That's fine, though. 2-to-1 transformations can't be performed deterministically, but because they have operator norm 1, they're a possible Krauss operator. Here I'm using possible in two different senses. One, it is possible to incorporate it as a partial description of a transformation, and by including more of a description, you can complete description of an evolution of a quantum system. And in that complete description, this transformation is one possible way in which the evolution can happen. Okay, so this gives us almost everything you'd like in representation for quantum transformations. The magic starts when you put the two types of observables together, quite famously, the interacting complementary observables. So the classic example is this gadget, where you've got a green node connected to a red node, and famously it gives you 1 over root 2 times the control NOT gate. Why 1 over root 2? Well, it comes in with what I was talking about, the operational meanings before. Here, this green node represents an isometry. You can perform it deterministically. This red node represents a possible Krauss operator. So a computational effect which could happen when you apply a map. And when you compose them, you get a possible transformation. So this two-node diagram represents a controlled knot which occurs with probability 1/2. Now, this is exactly what you would want for a model of computation in which these transformations, the operations given by the green and the red nodes, are the basic transformations of the computational model. And I, together with Ross Duncan, Dominic Horstman, and Simon Perdry, described an abstract model of computation in which you would do this, relevant to optical quantum computation and lattice surgery, which we call Pauli fusion. But models of computation like this aren't what most people use the ZX calculus for. They use it for things more like the circuit model, or for measurement-based quantum computation, in which you still have these non-deterministic effects, but still it's not the 2-to-1 node which are part of your computational transformations. So what about the circuit model? Well, most people would like this two-node diagram just to represent the control knot. It doesn't, strictly speaking, represent it. It's proportional to it, and you can do a lot by saying, well, it sort of works like the controlled NOT gate, and that all the scalar factors come out in the wash if you're doing certain tasks, like describing equivalences of unitary circuits. That proportionality scalar cannot be anything but a unit complex number. But if you're communicating to the outside world, if you just like to sort of reason precisely about things as well, you have to do a little bit more than this. Okay, and furthermore, we often describe it this way. That is to say, where we think of the green and the red as sort of not occurring at different points in time. Now, this is not a problem, but I'm just going to point out a particular thing about this, is that there's no defined input-output relation along this wire. Mathematically speaking, this is perfectly reasonable. Again, these are just tensor nodes. Operationally, however, we've lost the meaning of the individual nodes as operations that we perform on the state. Now it's only the composite, which is a meaningful transformation. And of course, if we're talking about the circuit model, usually it is the controlled knot rather than just the red node or the green node that we care about. This is all perfectly fine, but it means that we've left this domain where the individual nodes have an operational meaning. And this is something to notice when we think back about what was useful about having that, what led us to allow us to think about that. Okay. Now, if you want to describe what the control knot is in the standard presentation of the ZX calculus, you need that. So that's just a two-node gadget. And the only job that that has is to make the mathematics work out. It's an admission that the two-node diagram that we had before isn't quite enough to convey what we actually meant. And this sort of recurs within some of the ZX rewrites. Of course, this is just a sampling of them. Here we've got, again, two-node diagrams of this sort, whose only job is to represent a scalar factor. They are scalar gadgets. And if we take a look at what their roles are in the ZX calculus rewrite rules, what are these rewrite rules? Well, these rewrite rules are expressing the property of being a scaled bialgebra, which is to say a bialgebra, except for the fact that we need some scalar factors. And those scalar factors are the price of specialness. Okay, so is this actually what we want in a calculus if we were sort of designing this precisely for reasoning about quantum circuits? I mean, it's not easy to come up with these calculi. There are good foundational reasons for having thought about this. And as I noted, there's a very good reason to have this model for the ZX calculus in settings where you have the individual nodes actually represent basic transformations of your system. But for reasoning about quantum circuits, is this what we want? To have diagrams where we've got virtual particles to make the mathematics work out? Okay, so you can feel a little bit contemplative about that, but there's the calculus, the ZH calculus, sorry. Maybe this will do what we want. And actually, it starts off on a very strong footing. It's the natural string diagrammatic extension of the approximately universal family of Hadamard CCZ gates. Okay, it's only real valued, but of course, it can still encode arbitrary quantum computations. You can encode the complex coefficients that you see in most presentations differently using the Hadamard and CCZ model. So this is basically good enough for most people's idea of what quantum computation looks like. And it's a very strong motivation. We start off with some Z dots representing the same thing as the Z dots in the ZX calculus, only in this case, they're phase-free. And we've got H boxes, which are a higher degree generalization of Hadamard transformations, and where we add some parameters there to add some additional control. And these are the semantics for them. So again, like the Z dots of the ZX calculus. And here, these H boxes, they're a matrix consisting entirely of ones except for a single possibly non-one coefficient in the lower right-hand corner, having the structure basically like the Hadamard gate, the 2x2 Hadamard gate, with a small difference. So this is motivated more by counting complexity, I would speculate, than by physics. We don't have the symmetry between the Z dots and the H boxes that we have in the ZX calculus. This is not a problem for me. I'm perfectly happy with something that works from foundations of computer sciences to foundations of physics. We sort of see the power of the ZH calculus for reasoning directly about traditional classical computer science in this work that was presented by Konstantinos earlier this week. So does the ZH calculus do precisely what we want? Again, almost. Okay, so here's the motivation that spurred on the development of the ZH calculus. Here we have the presentation of a highly controlled Z operation. This is excellent. I mean, this is a nice symmetric diagram representing the symmetry of the operation. It's concise. There's a lot to like about this representation. It's very good. And for the Hadamard transformation, one qubit to one qubit transformation, we have this representation, which, okay, so I mean, it's a nice matrix. It's perfectly simple, but it's not unitary. Okay, well, we can work with that. But this sort of informs what happens with the rewrites as well. Again, here's just a sampling. And this is the price that we pay for the non-unitarity of the Hadamard gate in the ZH calculus, is again, these scalar adjustments, these scalar gadgets. I should add that that diagram on the bottom is not from the original presentation of the ZH calculus by Miriam and by Alex, but it's the one that's sort of implicit hanging around in the background. Now, it's not easy to come up with these calculi, right? I mean, this is a very good calculus, and it does a very good job. It's simple, it's well designed, but it's not precisely what you'd want for reasoning about quantum circuits, however good it would be for some other applications. Okay, you say, okay, you're coming across as pretty critical here. What actually would you like from this situation? You know, what are you actually aiming for? I would like to get rid of as many of these scalar gadgets as possible while remaining scalar exact for application to quantum transformations. Okay, like direct representations of these transformations which are expressed as simply as possible. I would like the rewrites for reasoning about these transformations to be as simple as possible. And the reason I want to hand wave so much when I'm speaking outside of this community, I want it to be easier to convey and possibly to promote these calculi by saying that, look, this does exactly what you would like. It expresses things exactly as you would like. and then it becomes easier to promote them. Can it be done? Well, yes, it can. What's the catch? Well, there's not much of a catch, actually. All you have to do is to give up the special status. So having these unit norm coefficients in the in the operators for the semantics might seem like a convenient choice, but it's actually getting in the way. What you can do instead is to consider different normalizations for nodes of different degree. Now, there are many ways in which you can do this. So there's a design choice inherent in this. I'd like to prioritize unitary representations for the simple operators, such as the controlled knot and the Hadamard. I'd like to maintain the symmetry, the unitary equivalence between the ZX green and red generators, because that represents an important thing about physics. And because these rewrites, the rewrites that we use most often, the bialgebra rule tends to be one of the most often frequently used ones, as well as things like the fusion rule. But bialgebras are the ones that have basically not quite come to the fore in these existing presentations. I'd like to have bialgebras on the nose in these calculi. And in order to convey what I'm looking for, I've called these well-tempered calculi. They're governed by nice geometric progression in their semantics, and they're tuned to reduce adjustments when you're actually performing with them. Okay, so if we're giving up these coefficients with norm 1, what instead should we do? Well, let's consider defining them this way. So here I've got some scalar nu. I'll describe what scalar that is in a moment. But in principle, you could just start with a parameter nu whose value you fix later. And here I'm multiplying the traditional of degree 1 nodes by nu and multiplying the traditional semantics for the degree node by 1 over nu. And I'm leaving the degree 2 node alone because that's already unitary. And we want to have nice, simple unitary transformations represented that way. The red nodes, we do exactly the same, only they're red nodes. And so this way we maintain the unitary equivalence in between the red and the green families. And if we do this, then if we choose the unitary representation of the Hadamard box, then we have the color change rewrite. It comes along for free. So this gives us everything that we want so far. I haven't described what you do for the higher arity nodes. I guess that will become clear in a moment what I do with those. But why nu and 1 over nu? Why change the normalization in different ways for different degrees like this? It's precisely so that we can have a fusion rule. And if you adopt a fusion rule like this, then it becomes clear what the normalizations for the higher degree nodes should be as well. So that the nu for the degree 1 node and the 1 over nu for the degree each other to give us exact unitarity when we have a one-to-one transformation. Set nu to be this particular value. This gives us that representation for the controlled knot on the nose, which again is aligning with our priorities of unitary representations. For the ZH calculus, so perhaps we can consider normalizing the Z dots of the ZH calculus similarly to the Z dots of the ZX calculus. Okay, so we choose this normalization. Again, we will end up getting the same fusion rules that motivated those normalizations for the ZX calculus. For the H boxes, we reverse the progressions of the normalizations. We start off with nu for the degree 1 H box, but then we increase the degree rather than decreasing the degree. Okay. Why would we do that? It's so that the decreasing degrees of the H boxes, the increasing degrees of the H boxes compensate the decreasing degrees of the Z dots so that we get an exact representation of the highly controlled Z gate. And if we take that same value of nu that we had for the ZX calculus, then the one-to-one Hadamard box becomes unitarily represented. Okay, so I mean, that's all very nice, but I mean, that seems sort of ad hoc. Well, these choices aren't actually ad hoc. They do come from someplace apart from giving us what we want in terms of the concrete representations of the operators. They actually arise from the rewrites as well. For the sake of presentation here and also in the paper, I prioritize the unitary representations, partly because I think this is important enough for reaching out to the community. But these same choices arise if you prioritize the rewrite rules instead. For every rewrite rule that you would like, if you take an idealized form that's free of scalar gadgets, then the soundness of that rewrite rule represents a constraint on your model, on the possible models for which it would be sound. And the normalizations that I've described here solve for the following rewrite rules. So for the ZX calculus, this is not all of the rewrites that I have. There are a handful more, but these are the important ones. And these are the ones representing the ZX calculus as in the bialgebra rule. And in fact, you might notice that this is an any-to-any bialgebra rule instead of just 2-to-1 or a copy rule. They're subsumed by this rule, as you have actually in the original presentation of the ZH calculus as well. And these rules also have simplified a little bit. There we have a scalar gadget in the Euler rule, but that's representing a complex phase. That's doing a different job. It would be nice also to represent that more directly, but things have improved there. Okay, and for the ZH calculus, here this is again just a subset of the rules of the well-tempered ZH calculus. Here, that's just the fact that the Hadamard box is unitary. So that's not a surprise. Here, this is a place where we do have a scalar gadget, but this is to be expected. This is expressing the fact that we no longer have a special commutative dagger Frobenius bialgebra. Yeah, so we're always going to have some sort of corrective factor there. That's just the sacrifice that we made. But now, here we have, in the H boxes, bialgebra rules on the nose and fusion on the nose without scalar factors. Now, you might say, well, this doesn't seem all that special. And well, that's the point. I'm not actually trying to make a theoretical advance. I'm trying to make a practical advance. I'm trying to make these as useful as possible to a wider community. But seriously, yeah, so this is what I was saying here. And in this work, it's not just showing this one solution. I tried to signpost for a range of reasonable possible renormalizations. I didn't sort of just bulldoze ahead. I tried to see what the scope of possible renormalizations were, what range you could use. And I even signpoint to some of the places where I've restricted beyond some interesting choices that, for example, would simplify the Euler rule. There's 16 pages of algebra there, which allow you to, if you want, sort of explore what happens with various simplified rewrite rules. So as an example, this is the constraint imposed by having the bialgebra rule on the nose for the ZH calculus. I won't explain what those U's and H's are. Actually, I will. It's short enough. They're just renormalization factors for White and Hadamard boxes. If you wonder if there's a better renormalization, you can use those 16 pages of algebra to see if you can find one. And if you find a better one, I'll use it. I'm motivated by practice. If you find one that's easier to use, I will use it. That's not something that I expected to still be there. Oh dear, what's going on there?
Can you slowly come to an end anyway, Niel?
Here we go. Sorry, yes. I'm putting this slide up here to say there's a lot more that I could say. I'm showing this slide to show you that I can talk about this if you like, but not now. So in summary, I wanted to present well-tempered versions of these calculi, which reduce the involvement of scalar factors. I showed how it can be done, and I tried to do it as well as possible by building on what I perceived as the motivations for these calculi, building on the original selling points of the ZX calculus, the interaction of complementary observables, now precisely bialgebraic, and strengthening on the distinctive features of the ZH calculus as I saw them, by trying to bring the white nodes and the yellow nodes, again, into a bialgebraic relationship with one another. The full details are there. Those are the most important pages of the paper. Pages 2, 3, and 33 if you read no others. 11 and 12 have some remarks you might find interesting. Thank you for your time.
Thank you, Niel. I will post in the Slack so we can all applaud on my applause if I find the right emoji. There we go. Okay, so we have, yeah, we're slightly over time, but I think we have time for 1 or 2 quick questions. So in the Slack, Konstantinos asked that when I construct a tensor net from a graph-like description, so nodes with their tensor types and an edge list, then I need to choose a foliation of the diagram and go to stick the appropriate normalization. I think the question, like there's a note afterwards which says, does it matter which wires are input and which are output?
No, so this is something I didn't explicitly say, but I also designed these well-tempered calculi to be symmetric as the ZH and ZX calculi are. There's no particular input-output relation for any of these generators. I think that this is an important feature.
Thanks. And Giovanni and Ross, I think those 2 questions are related. They ask about fusing spiders. So Giovanni asks about the special rule for, I guess, doesn't specify whether it's for ZX or ZH. And Ross asks about the spider theorem and self-loop cancellation.
Yes, so here I'll this slide. If you take a look at pseudo specialness, yeah, so loops do not cancel in this version of the ZX calculus, or the ZH calculus for that matter. They introduce scalar factors which, according to your preference, you can represent either by a solitary degree 0 green dot or red dot. I introduce new boxes as a way to try to more explicitly represent scalar factors in the ZX calculus. Of course, the ZH calculus has no such problem. You can explicitly say what scalar factor you mean. Yeah, so this is a sacrifice that you can make. In this case, the special rule is something which is nice. It helps to simplify diagrams, but I haven't found that it comes up as often as bialgebra. And so this is a sacrifice perhaps that you're not willing to make. Perhaps in your applications, it's more important for the calculus to be special. For mine, it isn't.
Okay, thank you very much, Niel. And let's end the talk here. Bye.
Thank you.